Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to discuss about the design shear strength of steel beams. So before we proceed for the design shear strength, first we need to understand the stress distribution, shear stress distribution in case of beam section. So the shear stress distribution in a beam section can be given by tau is equal to VQ divided by IB. So here V is the applied shear, Q is the first moment of area of the section beyond the point at which we want to calculate the shear stress. For example, we have this section, rectangular section. If we want to find the stress value, shear stress value at this point, at this location, at a distance y from the neutral axis, then this much area which is away from this point or away from this section, which has a depth equal to, if this total depth is h, and if we call this depth from the neutral axis up to the extreme fiber equal to c, so this depth will be equal to c minus y1 or y. So the first moment of area Q will be equal to area mean B times c minus y1. So this will be the area multiplied by the moment arm, so from centroid neutral axis up to the centroid of this shaded area, so which will be equal to c minus y1 divided by 2 plus y1. So after solving this, we can get Q is equal to B by 2 times c square minus y1 square. So this will be our first moment of area of the section, which is away from the point at which we want to calculate the shear stress value. So if we see this expression Q, so this I is the second moment of area and B is the width of the section. So if we want to see the distribution of this stress in the section, so I can replace this equation. Now we can replace this Q with this expression. For example, I can write that tau is equal to V times B by 2 into C1 minus, C minus C square minus Y1 square divided by I into B. So here Y1 is the distance from the neutral axis. So when the distance from the neutral axis, or if we want to find out the value of the stress at the extreme fiber, so in that case this y1 will be equal to c1 and this factor will become equal to 0. So at that point the tau will be equal to 0. So as we keep on decreasing this value, mean we are moving toward the neutral axis. If I want to calculate the stress value near to the neutral axis for this point, so y will be this one. So as we keep on decreasing the y value, mean we are moving toward the neutral axis, so this factor will continue to increase. So when this factor is increasing, so it means the stress value is increasing. So as a result, we will have the scenario like this. In case of rectangular section, at the extreme fiber the stress will be, shear stress will be 0, and at the neutral axis when this y1 is equal to 0, so we will have the maximum value of this tau value, stress value. So its distribution will be like this. So maximum value will be at the neutral axis. The reason is when we substitute the value of y equal to 0, mean we want to find out the value of shear stress at neutral axis, so this y1 will be equal to 0 and we will have the maximum value of stress. And when we want to calculate the stress value at the extreme fiber, so in that case this c1 and y1 will be same and we will have this factor 0, and as a result stress will be equal to 0. So this is opposite to the flexural stresses. In case of flexural stresses, we have the maximum value at the extreme fiber and minimum value or 0 value at the neutral axis. So shear distribution is opposite to that. So if we see the distribution of the shear stress in the I section, so we can see here there is a negligible stress in the flanges, and the stress in the web is significantly high. So we can say that the flanges are ineffective to resist the applied shear, only the web is resisting the applied shear. So the area which is resisting the applied shear is will be equal to the area of the web, and it is given by area of web is given by d times thickness of web. So the part to accommodate for the contribution of these flanges to resist the applied shear, so we can consider this much portion of the flange, and we can include this much portion in the area of web. So instead of taking this h value and h multiplied by thickness of web, we can consider this total depth of the section multiplied by the thickness of web to calculate the area which is resisting the applied shear. Okay, so in case of stable webs, if we are talking about the compact section, so in case of compact section, there will not be any local buckling of the web and crippling of the web. So in that case, the web can reach up to the yielding stage. So if the web reaches up to the yielding stage, so in that case, the nominal capacity of the web can be given by Vn is equal to tau y area of web multiplied by Cv. And here this Cv is the shear coefficient, and it is the ratio of critical web stress according to linear buckling theory to the shear yield stress of the web material. So here if we see this tau y is the yield shear stress, and it is given by, or we can approximate it as a 0.6 times Fy, mean we can approximate it as a 60% of the tension yielding stress, the shear stress of the material. And area of web, we have already defined what is the area of web. So in that case, we will consider the total depth multiplied by the thickness of the web. And Cv, which is shear coefficient, so it is given by it is governed by the type of buckling of the web. If the section is compact, so in that case this Cv will be equal to 1, and if the section is non-compact, then its value can be calculated, and similarly for cylinder webs, its value can be calculated from the formulas given in the AISC code. So here, as we are talking only about the compact section, so in that case, if h over tw is less than this value, so we can say that Cv is equal to 1. And if we talk about the design shear strength, so this nominal shear strength multiplied by this phi factor, phi v, this will be equal to the nominal shear strength, and here the phi factor is equal to 0.9, because we are considering the yielding of the section. So when the material or the steel is yielding, so in that case we can take this phi factor is equal to 0.9. So the nominal, so the design shear strength of the section can be given by phi v Vn is equal to phi v tau y area of web times Cv. And in case of compact section, we can write that phi v 0.6 Fy times area of web, and this should be greater than Vu, applied load. If this design strength is more than the applied shear stress, so in that case our section will be safe against the applied shear. Otherwise, if this design shear strength is less than Vu, mean applied shear stress or strength, applied shear force, so in that case our section will be unsafe.